Now this video is just really about concept building. We want to start out with a function of two variables or more, and we have to start in saying what is the multivariable calculus version of a closed interval. Well, first off, it can't go on forever. Closed intervals don't go on forever. Whatever region we're looking at can't go on forever. And so the first thing we're going to talk about is a bounded region. Now, these are all listed in the notes, so I'm just going to sort of talk my way through it. A bounded region is a region in the xy plane that you can draw a circle around. So for example, if I'm looking at this strip in here, that's not bounded because no matter how big a circle I draw, I can't actually get every point in that region. On the other hand, if I have a region that looks like this, which seems to happen a lot, that's a bounded region because I can draw a circle around it. So first off, it has to be bounded. If it's not bounded, there's no guarantee that it's going to have a maximum or minimum. And that's the only thing we want to do is the analog in Calc 3 of Calc 1. So it has to be bounded. Now, it also has to include all its boundary points. Well, let's talk about a boundary point. In order to talk about boundary point, we actually also have to talk about interior point. Now, in a closed interval, we had to include everything between those two, and there were boundary points, and we didn't think of them as boundary points, we just thought of them as endpoints. Well, here, it gets a little more complicated. Let's draw the region that I said was bounded. That's this one here. An interior point, we'll talk about this first, is a point where you can find a circle and draw it around that point, and then the whole circle and the inside of the circle, that's called a disk, stays inside the region. So for example, that point there, right here, is not an interior point because no matter what circle I draw, it won't stay inside the region. Let's draw this point right here. That is also not interior point because no matter what circle I draw around it, I can never get that circle to completely stay inside the region. However, this point right there, that is an interior point because I can find a circle, not every circle, but I can find a circle so that the whole circle and the inside of it, that's a disk, stays inside the region. So that's what we mean by interior point. One where you can draw a circle and the whole circle stays inside the region. What's a boundary point? Well, a boundary point is a point where every circle that you draw around the point hits the region and hits points not in the region. For example, this one right here. No matter what circle I draw around it, no matter how small, every circle is going to hit the region, and every circle is going to hit points that are not in the region. Now, why do I even bring that up? Well, in order to actually do the calculus version, first off, it had to be bounded. That means you have to be able to draw a circle around it. It has to include all of its boundary points. If it doesn't have all of its boundary points, then there's no guarantee that it has a maximum or minimum, and calculus just won't be helpful in finding it. So it's got to be bounded. It's got to have all its boundary points. So for example, every point on this triangle has to be included, or there's no guarantee that this function is going to have a maximum or minimum there. In mathematics, the next math class after this is Math 420, and you'll talk about closed sets. A closed set is just a set that contains all of its boundary points. We won't worry too much about the topology that was actually invented to have to deal with this. But the kind of regions we have to deal with, if we want to find a global maximum or minimum, they have to be bounded. We have to be able to draw a circle around it. Every boundary point actually has to be in the region, or there's no guarantee. And this triangle with the inside is very typical. All right, so that's going to be what we have to assume we're looking at when we try to find a global maximum of a function of 2 or 3 variables.